now we are doing something different. It's about sport. Or something like that. So it is,
about humans.
But we, you will be surprised, it's not that far from robotics as you may think. So thank you. I'd like to introduce Joachim Dörfer and from Technical University of Munich, and yeah, the stage is yours. Sorry.
Thank you very much. Thanks a lot. Thanks for the invitation, Michael. Nice to be here. As Jan said, this will be a new perspective now. I will talk about humans. I will talk about how humans behave in everyday life when they manipulate objects, when they use tools. And I will also address particularly address the aspect of quantification of this human behavior, right? And then, of course, this meets robots who may actually try out to do the same task and eventually may fail in the same way as the patients I will show you. And I would like to introduce this in just give you a little bit of introduction to apraxia, which is here both below right, you see a definition. It's a neurological disorder of skilled movement that is not explained by deficits of elementary motor or sensory system, right? So a problem with executing actions, doing movements, but not really related to basic primary motor problems or sensory problems or problems of understanding the task, etc. This is the book of Georg Goldenberg, my mentor, so to speak, in this, who actually highlighted that apraxia is the cognitive side of motor control. And so to explain you how this was introduced, a little look back to Hugo Lippmann, who, so to speak, invented or was the first person to actually report about apraxia, 1908, the left hemisphere and the action and acting. He did kind of a first experiments in patients, and actually he looked into patients with head and hemiparesis on the left side of a body or on the right side of a body. And you see which tasks these patients had to execute: expressive movements like threatening, blowing a kiss, military salute, pantomiming movements like count money, play a barrel organ, so a task which is not very well known nowadays anymore. Pantomime of intransitive movement like swimming, or also, and that's most relevant for us, real tool use like combing, sealing a letter, sticking a stamp, and so on. And now, his observation was that patients with paresis of the right hand, so patients with damage to the left brain, you know, the motor system is contralaterally organized. Patients with damage to the left brain performed errors with the ipsilateral left hand, so with a good hand, with a non-paretic hand. Okay? So problems in this type of tasks which were not related to basic elementary motor problems. Early observation. And now I immediately go to show you some examples. Previously, okay. Just some examples of this apraxia. So that actually these questions which nowadays you also would have problems to remember which would be the correct movement and so on. Good. Good. Pantomime of tool use. So this patient is requested to show how to use a saw, and he has problem, he has apraxia, and in the video you can see that he performs a movement which is repetitive and reminds somehow on sawing, but it's not a sawing movement, right? We put the saw here so that he could actually really understand, but he is not able to really produce the right movement in this pantomime condition. So show me how to use an object. Good. That's pantomime. That's another example of a patient, again, who has huge problems in showing the pantomiming of this task. I skipped this, and I also show you here that he also has problems with using the saw, right? So even in the real context, with the object, with the tool, with the recipient, he actually orients the saw according to the axis, long axis of the stick, and then somehow insists on this, right? When he gets correction, and still the movement is not really fluid and quick, right? So obviously, even after finding the solution, he still has problems to execute the task. Okay, I'd like to continue a little bit with some examples because I think it's interesting. So in this particular study, we tested now really the dependency on the conditions of doing this. So we had a situation when we asked the patient to pantomime, and with a patient when we ask a situation when we ask the patient to really execute the task, and a kind of intermediate situation when we ask to demo, but without actually grasping the tool. Okay, I'll show you how it looks like. So this patient has apraxia, so actually you should see he is not able to produce the correct pantomime. And you see as, again, repetitive task, but that's not hammering, pretty clear, right? But if he is asked to just demo with the hammer, but without the other context, he can nicely do so, right? And also in the real context, where not a big surprise, he's able to actually perform the right task, right? Exactly. So this is wooden materials because we did some magnetic recording, but I'll go to this later on. Just to remind you, this patient moves with the left hand, as you see, right? Because these are patients, as I said, with left brain damage. The right hand often paretic, right? So not usable frequently, but the left hand would be the good hand, so he performs these tasks with the left hand, fails in pantomime, but quite perfect with real use. Now, a patient with more severe apraxia, and again, you would see that he's lost with a pantomime condition, right? So it's not so clear what we want with a hammer from him. In the demo condition, interestingly, he grasps the hammer correctly with a functional grip, even if this is quite complex, but then is not really able to perform a hammering movement. And most interestingly, in this condition with a complete context, right, see what he does, right? So he uses the hammer and he presses against these little pegs, you know? So obviously, he knows what he should do, right? So obviously, he knows that this peg should go into the wood, right? But what he's obviously not able to evoke is the correct movement, the correct manipulation, right? So you would say here that functional knowledge is preserved, probably, but manipulation knowledge is impaired in this particular case. Good. Well, what do we do with this? How do we quantify this performance? We take the videos and we score these videos, and usually we have like descriptions like here. So in a situation of hammering, for example, was the grip okay? Was it a tight cylinder or lateral grip? Was the movement correct, up and down movement from the elbow? And was the orientation of the whole movement okay? Movement has to stop before touching the table, right? That's the way we would score, quantify such a pantomime, but also a real tool use condition. And if we do this, we can find results like this. So here, that's the performance of patient controls with the left hand, controls with the right hand, LBD, you will see this abbreviation more frequently, left brain damaged, LBD patients, and RBD patients with right brain damage. And what you see here is what we expected, that particularly patients with left brain damage don't reach maximum score, right? So have a reduced performance in our tasks. And this depends on the condition, with pantomime being most affected, the demonstration somehow intermediate, and use less affected, but still significantly compared to normals, particularly here for the hammering condition. Okay? So we tested two tasks. One was hammering, the other one was ladling. Good. So far, a little bit about introduction to apraxia of single tool use.
Questions allowed?
Sure. Sorry.
Okay. thank you for allowing the question. I just wanted to ask whether or not you asked them whether or not they were right-handed naturally or left-handed, because I think 90% of the population or so are right-handed. So if they have, for example, if I imagine myself using a hammer with my wrong hand, I would also kind of struggle maybe, because I didn't practice the movement during lifetime, and these were all elderly patients. So
that's correct. I mean, you have to be aware about that. If you do this with a non-dominant hand, you'll be not so skilled, right?
Yeah.
But the errors we see is not really attributable to handedness, right?
Okay.
So it's just more severe errors, but you have to be aware about this. About left-handers, that's a big and interesting topic. We have to exclude them usually, right? Unfortunately, because this minority brain is organized differently in left-handers. It's not just a mirrored right-hander, right? Not in the brain representation, not in terms of hand use, right? Left-handers normally are better with both hands, etc., right? So it's interesting, but I'm talking about right-handers, so to speak.
Okay.
Good. Now it comes to the common topic, which is daily activities, right? And so I'm going now into activities of daily living, ADL, and show you how apraxia looks like in these patients. So that's a patient now in a more complex situation. The task is to cut a piece of bread. He also now has to do this with his left hand, because the right hand is paretic and pelagic, right? So not usable. So there are some helps, like from occupational therapy, you would have some rubber so that things don't slide easily, etc. But I show you now the problem of this patient. Cut a piece of bread with what you find on the table, right? And the problem here is that he uses the wrong object, the wrong tool, tries with a spoon, tries with a fork. And somehow he gets aware that this is the right tool, you know, but still you saw just quickly that still the movement was not correct, right? He pressed instead of slicing, right? So problem in correct tool as well as correct movement. And one more example, different task, punch and file a sheet of paper. And again, we have, in this case, a young stroke patient. That happens also.
Können Sie das für mich machen? Ja, ja. Genau, dann dürfen Sie anfangen. Alles, was Sie brauchen, ist auch bereit.
So the left hand is the hand she has to use. And the task is also clear, right? So we have the correct tool to punch the paper, and the distractor tool, which is not related to the task. And she finds a solution, right, but neglecting the correct tool. Maybe you also did it like this sometimes in your life, I don't know, but that would be an apraxic error. Okay. Yeah, and so wrong tool, but good. Well, now how to score, how to quantify these tasks. So there is kind of a tradition how to do this with rules that had been somehow brought from one author to the next. In principle, that's something I guess you all know from your daily life and from the work in so human factors. You have a certain task like making a cup of tea, and then you can create these sub-levels of sub-tasks and going more and more into single elements of movement, right? So that's how such tasks are created, as all those who work with Michael know. And of course, with a lot of variability, a lot of solutions, etc. Right? And as I said, there is a system how to deal with this, which has been developed by therapists mainly and by people who know this. And so that's the current solution to score these videos and try to find and define the errors, right? And here we have the errors which you could expect during tasks like this. And in principle, we have 3 different classes of errors. We have sequencing errors, so errors which are related to the sequencing of the substeps, like adding something, making a wrong anticipation. Perseveration, something we see frequently in patients. They do things repetitively, right? Which they would need to do only once. A real sequence error, so wrong action at the wrong moment, and omitting a subtask, etc. So that's sequencing errors. And conceptual errors would be, so in principle, more fatal errors, omitting a gradient, putting a gradient which actually is not necessary, so substitution, misestimation of quantity, quality error, etc. And finally, we have this error class, spatiotemporal errors, which is defined as errors in the execution or mislocation, right? So errors of a movement in space and time. So this is how we quantified videos like this, and to give you just one example of the results, if we look into this and have bigger group of patients, we now find, for example, that we have 2 tasks here, and we have patients with left and right brain damage and control subjects. And what you immediately can see is that, yes, there is a difference, so more errors in patients with left brain damage, right? But now also patients with right brain damage actually have problems in this task. So these are the red bars here, right, compared to the controls. So now also the right brain is obviously engaged. Actually, there is not a big difference if you look carefully. Also the different error categories, right, you see that errors, patients with left and with right brain damage, they have sequencing errors, they have many conceptual errors, they have some spatiotemporal errors, right? And same in both tasks, although there are massive differences between the different tasks. But this is what we analyzed behaviorally from this data and from this video. Just to give you a quick idea of what you now can do if you want to look into the brain, you have technology to actually associate errors with brain lesions. And this is the technology, lesion analysis. There are some software. And what you do is you take the lesions of patients. So 29 is not a big group, so it should be bigger in the best case. But that would be just the overlay of the lesions. So where do these 29 patients have the lesions? And left brain, as I said, it's again only left brain damaged patients. And most of them had here lesions frontally or parietally and everywhere. Now, this is just the sample. And what you do now is voxel-based lesion symptom mapping. So you associate each voxel in the brain, whether it is voxel a little volume element in the brain, whether it's lesion or not, to the question, is there a deficit, yes or not? Okay? So association between lesion and deficits. And what you end up is in graphics like this one, right? So for example, you have here for document filing, yeah? You have the green area would be those areas in the brain which are in which very frequently there is a spatiotemporal error, right, during document filing. So obviously, this aspect of the task is solved or processed by this part of the brain. Conceptual errors during document filing are processed in big parts of the brain, frontal and temporal lobe, and the sequencing errors are processed obviously in the parietal part, since when there's a lesion there, patients fail. That's the logic of this approach, right? And you see that it's indeed more or less the whole brain which is somehow involved in tasks like this. So we have a very famous publication some years ago which is called You Need the Whole Brain to Make a Cup of Tea. And this is what we also see here. Right? For the tea-making task, the pattern looks quite different. What is remarkable here is just this little spot here. This spot here is related to sequencing errors in both tasks, right? So obviously there is a little area here in the parietal lobe, which is really related to errors in making the correct sequence of the subtasks. Good, so just a little excursion to how we can study the brain, so that you have an idea. And this is the final video of this part. It's quite, I think, impressive video also because how it's taken. So this is eye tracking. So a patient has this eye tracker, right? And you know there's a camera built inside. And so you now see a patient trying to make a cup of tea with his left hand from the patient's perspective, right? So from the self perspective. And the gaze location is indicated by this point here, right? So the red point shows you if a patient is looking to during performing this task. And you will see that in the end he fails in the task of making a cup of tea with milk and sugar. And he's trying around, he's looking around, and he is hesitating, as you can see. Okay. Okay, so that would be instruction to make a cup of tea, milk and sugar. And now he starts to inspect the objects with his gaze, right? So he looks at objects. That's complex kettle, not easy to open, admittedly. He looks at the coffee, which is a distractor, so that's not needed in this task, of course. Usually the eyes are in front of the hand. Probably you know this, I think, right? So you can nicely see that he looks at something and eventually he may touch it or he may not touch it. But the eyes are always time-wise in front of the hand. Well, of course, now that's not the correct solution. That's an error we see actually quite frequently in the praxic patients, right? But he's also insecure that somehow something is missing, and that's correct, right? So indeed, the water is missing. And that's the relationship. Yes, the water should go into the kettle, but unfortunately he doesn't realize this, right? So he's close, but... And this goes on, right? So he was not able in the end to make a cup of tea for his own. Was also quite young patient, and usually his wife was then responsible for all his daily activities, of course. Okay. So this is apraxia in daily life. It's not only related to left brain damage, also to right brain damage, can have many reasons. And I think it would be extremely interesting to have these scoring systems, which you are using sometimes, the automatic systems, to understand maybe even better with a taxonomy what actually is the problem here. Good. Let's skip to the second part, which is on kinematics. Well, kinematics now is quite established if you study movement disturbances in patients. And typically you use it to quantify and study paresis, spasticity, ataxia, tremor, sensory deficits. Classically use it in the paretic hand or the ataxic hand in patients, so in the affected limb. And classically you use it more in simple movements like aiming, reaching, grasping movements. Okay? And you see the number of publications. If you just search for stroke and kinematics, you see that it has increased during the last year. Now it's a quite high level of ways how you really demonstrate how people move in these situations. And that's just about technology. Maybe most of you know, so there is this optical camera-based systems to measure movements in robotics or AR situations, VR situations, virtual reality. People frequently use this type electromagnetic trackers, which have to be also put to the limb. And then you move in this magnetic field, and you can very precisely measure where this tracker is. As a simpler system, ultrasound system, which we used for a while, which was very good for our purpose. And now, of course, nowadays you have the markerless tracking, right? So you can actually detect movements without any markers and any special equipment besides cameras in the end. Yeah. So that's our various technologies. Now, just recently, there has been a big step clinically into the success of this idea to really quantify movements in the context of stroke recovery. So there was this recommendation of consensus group. So they said you should actually quantify performance of patients with kinematics and dynamics. And in particular, it was this drinking task by a colleague in Sweden, Alt Murphy, who really suggested that we should use with kinematics into these daily activities like drinking in order to understand the recovery of a patient from a stroke, for example. And we and some others actually extended this now one step further and went into more complex ADLs, more complex activities of daily living. In this case, we use optical motion tracking. So we have these cameras which gave infrared light, and we have markers placed on the hands. And the video will show you how this works. Probably most of you know. Anyway, so we just have two markers, so to speak, each on one hand. And you see the trajectories that are recorded from daily tasks, like this drinking task. Okay. Good. So that's the basic idea. And now since a few months we have the chance to also do this in a real looking like kitchen. So I understood this is a kitchen competition also here. we had one yesterday, and we saw the one of Michael, and that's our kitchen from Küchenplaner in München. So some of you may know it. It's this block, and of course it's important for us that we have this situation here when people prepare things and food in the middle, and we have the cameras on the ceiling that actually now are able to precisely record the movements of the markers. Okay. Good, and then that would be an example of such trajectories. We have the task of making a cup of tea, and you see the trajectories in 3D in a young person, in an elderly person, in a patient with stroke, so cerebrovascular accident, right? And you see how he moves around. So that's just one sub-movement during such a task, which is grasping the kettle, right, and moving the kettle. And you see the velocity profile corresponding to this movement here. And well, you already could see that if you compare velocity profile of the young with that of the elderly, that the duration is longer, right? That the velocity maxima are lower, and that's particularly true for this patient here, right? So prolongation in time, lower velocity, etc. And if we use this technology, we have published some pilot results. Now we are going into bigger groups at the moment, but this is only for few patients, and some elderlies and some youngs. That's the task, and this is the parameters we calculate from the trajectories, and there can be many parameters, so maximum velocities, mean peak velocity. Relative activity would mean how much of the time you do nothing, right? How long of time your hand rests. And other parameters, and that's just some results I would like to show you. So here we see the duration of this task, and this is a young group, elderly if they are requested to do it unimanually, and stroke patients doing it with a good hand, with the ipsilesional good hand. And what you can find here, for example, that, elderlies, seniors need longer, right? And stroke patients need even longer. These particular bars also show the relationship between movement and no movement. So gray would be the time when actually there is hesitation, rest, thinking, no movements. And you see that this time is also relatively increased, particularly in stroke patients, right? But also here not so much in elderly. This was not significant increase. If we look at this relatively, but clearly increased in stroke. One can look at the peak velocity, and you see that, actually elderly speed up if they are requested to do it with just one hand, right? Which is not possible for the stroke patients, despite its non-paretic hand. And path length is quite interesting parameter, so that's just how many meters you move around during such a task. That's a nice parameter, which actually is increased in the elderly if you compare it with young people. And that's another, from another sample actually, but just to give you an idea, of course, it's extremely interesting also to look at both hands. Okay? And there are parameters which actually can compare both hands. There's a parameter which compares the path length of a dominant versus the non-dominant hand, or a parameter which actually calculates how much of the time actually both hands are used simultaneously, right? And not for a big surprise, for example, if you have patients here, so for full patient group and for left brain and right brain damage, this time of synchronous movements of both hands is clearly decreased compared to young or elderly controls, just as an example. Right? So we can study the aspects, right, of the task with kinematics. And what is the next step, which is quite interesting now, is, well, kinematics is also something you get with the wearables, as you know, right? You get accelerations and you get rotation, velocity with the gyroscopes. So the question is, can we use wearables, right? So what we saw gave objective data, sensitive data, gave new insight. What about wearables, right? And yeah, you know, wearables and a chip, which is extremely attractive too. If you use a wearable in a daily task, this is the signal what you get, right? So that, of course, that's very noisy, right? You have acceleration changes all the time. So it's questionable how good this signal is compared to the measuring of the trajectories, which I showed you before. Yeah. Okay. And one example recently published is we used the wearables, so the smartwatches, here with seniors, and try to understand whether we can actually kind of quantify or classify the level of frailty in the seniors. There is a famous frailty score, which is classically used, which looks into weight loss, low physical activity, grip strength, slow gait speeds, and self-reported fatigue, right? And we compared our watch measures with this frailty score in 2 different daily tasks, which we did in the lab, right? So one was planting a plant, and the other one was our making a cup of tea task. And these are the results. So here we have the 3 groups of the seniors. Robust means healthy aged, right? So aged, of course, but healthy, so not particularly manifestations of frailty. And then we have in the middle of a pre-frail group, and F would be for frail seniors. And here you see the parameters which we extracted from the wearables, right? And from the smartwatches. And what's particularly interesting here is that duration of the task was not informative, right? So both groups of all 3 groups used more or less the same time to do the task, so that didn't help to classify. But we had other parameters, like this one, so the peak acceleration, and the standard deviation of a peak acceleration, which actually then gave a nice classification of robust versus pre-frail and frail. And also this parameter, which is about the smoothness, counting the number of velocity peaks per second, was also very informative about frailty, right? So picking the right parameters out of our data enabled us to somehow quantify frailty in daily life. And that's, of course, interesting because now you can do measurements every day and see the continuation, so how longitudinal, what happens, and eventually could intervene when it's necessary. Good. Now, of course, with IMUs, with wearables, you are very close to real life. This task I showed you before was lab. But now what happens if you send people out of a lab at home? Can you still gain information during daily activities, right, from our data? And that's recent work when we actually used same with Huawei watch, now with both hands in patients with stroke, during just 1 day of life, right? In this case, 1 day in the hospital during therapies, lunchtime, etc. So a few hours during 1 day. And in this case, we compared the results for the left and the right hand, so for the paretic and the non-paretic hand in these patients. And what you see here is for just 3 examples. So healthy subject, a patient with moderate paresis and a severe paresis. The agility measures, so the standard deviation of the angular velocity peaks, right? So agility, as we call it, during the day, right? And so there was some low agility, then higher agility and very high agility. And it's not really very surprising. You see that healthy subjects have with both hands similar agility. In patients with moderate paresis, that's lower, and it's even lower in patients with severe paresis. What is interesting clinically is that we have this clear difference in patients with severe paresis. So it's clear that one hand is really bad, right? And so you don't use it logically. But in patients with moderate paresis, it seems the performance is quite similar in both hands, meaning that eventually also the good hand suffers, right, from the disadvantages for the paretic hand. And just another parameter, movement smoothness, which develops more and more to be a very prominent and important parameter in this field. Again, smoothness now would be better if it's smaller. And you see that particularly for the paretic hand, you have very high values, so low movement smoothness. So with these world recordings, we can get some sensitive information. And I'm coming to my final part, which, how long do you have? 5 minutes or so? Or, yeah. 10 minutes, very good. I need 5. So now the final question is now, okay, how is now this kinematics, right? How is this related to apraxia? Right? So someone who performs praxic errors, right? What about the movements? What about the fluency, the smoothness, the agility of the movements? And we performed many years ago one study which was on an aspect of apraxia which you have not seen yet. It's on imitation. So patients with apraxia also have problems with imitating meaningless gesture which we show to them, right? So they, the therapists show them a gesture like this one. Yeah, that's the gesture. And you see that this patient fails to imitate the correct gesture. Right? So that's a famous, one other famous symptom in apraxia. And again, I'll show you a little video, which makes it even clearer how this looks like. So apraxia of imitation of meaningless gestures. And again, he does it with the left hand, which is his good hand. The examiner also does it like in the mirror, so with the other hand to make the task simpler. And you see he can't do it, right? So he's unsure. He knows that that's probably not correct. So he asks, "Is this right?" etc. Right? So problems in imitation. And in this very, very old study, actually, so this was a brain paper, 96, a while ago. What we showed was that. Or what we tried to find is what is the relationship between the correct imitation and the kinematics, right? And for the kinematics, we show here the velocity profile of this movement from a starting position of the table to the head, right? And probably you all know how a good velocity profile of a human stop movement should look like. It should look like a bell-shaped profile with a single peak, right? So that's a perfect start-stop movement, right, to a correct position. So this is what we found, association between correct imitation, nice kinematics. That's the other association, which is fine, so unexpected, bad imitation, so that's not the correct gesture, right, and related to bad, multi-peaked, hesitating, long kinematics. However, we also found dissociations in both directions. So here we have a correct imitation with a slowed movement, okay? And here we have the probably most interesting aspect, which is a nice kinematics, beautiful velocity peak, but the wrong movement, right? So the wrong imitation, so the wrong end position. So we have associations and dissociations, and this is what we also had in our full patient group. So black and yellow would be the association, right? So bad kinematics, wrong imitation, or good kinematics, good imitation. Or green and blue is dissociations, and you see it's nearly equally distributed. Just recently, we did the same analysis with pantomime. That was an interesting study when we tested for support with augmented reality, whether we could help patients with actually giving them very salient cues. I can't go into this, however, but still I show you our cues, right? So we showed them cues with a HoloLens of a hammering, right? And so we had 3 conditions. One was a 2D condition, just showing a picture of a hammer, and 3D was holographic animation of a movement. Actual was real use, right? So here we have 3 conditions, and here we have the kinematic variables which we extracted from the movements, right? And so there are 10, quite a lot, right? And the color here just shows the correlation, right? So do we see a correlation between errors in the pantomime and the kinematics? So how fluent, how good kinematically did the task? And you see, so red is good, red is certain high correlation, and we found relative high with a coefficient of 0.6, right? For 2 tasks, namely hammering and ironing, and for 2 parameters, one was the number of peaks per meter, so a smoothness parameter, and the other one was the relative time with a velocity higher than 0.5, so kind of break time, hesitation time. So this would be these parameters here. So for these parameters and for these 2 tasks, we had decent correlation between kinematics and failures, but you see in general it's task related, so nothing like this in our watering flowers task. So you can really rely on that movement which is performed kinematically perfect is also correct. And that's my last slide. Well, so we were able to actually code and score the apraxic errors, right, with our system. New approaches would be welcome, but still a reliable cognition needs semantic understanding. So we cannot just come and blindly measure kinematics and then say, okay, this action was wrong, right? We may have perfect actions with wrong kinematics and other way around. Right? Kinematics is sensitive to reveal sensory motor and cognitive deficits. We were successful with the IMUs, I would say, so they can be used. And we may even be able to do some world recordings with or without actual recognition in the future. We'll see how far we go. But of course, that's also a big topic now for the future in this field of neurorehabilitation. These are people I have to thank, in particular Philipp Gulde and Stefanie for the last works. Thanks for your attention.